Hi there. Today we're going to continue our discussion of phasor circuits, and we're going to analyze some more circuits that are based on alternating current stimuli. My name is Vivek Subramanian.
I'm Michel Maharis. Let's get started. Okay, so first off, we thought we would kind of give you the formal definition of a term that you saw in the last module, which was impedance. Okay, so impedance is the ratio of the phasor voltage to the phasor current.
So if I understand correctly, Michel, if impedance is just voltage over current, resistance is a specific form of impedance then.
Yeah, it's a subset, right? So the general form for impedance Z includes a real part and an imaginary part. The real part is in fact the resistance, right? That's in fact the real part of the impedance is always a resistance, and it is exactly in ohms. It means what you think it means. It's exactly right. But impedance also captures something more broad, or something different, not more broad. And that different part is something called the reactance, which is the imaginary part.
Wait, so hold on. So if I take that, a resistor has an impedance, but it's just the resistance. A capacitor has an impedance, but it's just the reactance.
That's right. Capacitors and inductors have purely imaginary impedances. Resistors have purely real impedances.
Got it.
And there will be circuits that will have combinations of these, general devices, things in a black box.
Or, for example, a combination of a series resistor and capacitor will have the resistance contributed by the resistor and the reactance contributed by the capacitor.
That's right. And in a sense, the resistor is telling you something about how that general component is burning power into heat, and the reactance is telling you something about how that general component is storing energy.
Got it.
That's another way to look at it. Now, just like we had 1 over R before, and that was conductance, we can have a generalized reciprocal of this called the admittance. And admittance is just what you would think it is. It's just current divided by voltage. It's just the inverse of this. So there's nothing really new introduced by this. It's 1 over Z. And it will also have G,
which is the conductance,
and that's as before, which is the real part of Y, and B, which is susceptance, and that's the imaginary part. Now, please do not take 1 over R and put it there, and 1 over JX and put it there, right? You have to take a reciprocal of Z and do that properly.
Yep.
Okay. And then as a summary of what you already know, here are for the 3 common things we deal with: resistors, inductors, and capacitors. This is the impedance, R, J omega L, and 1 over J omega C. And the admittance would be 1 over R, 1 over J omega L, and J omega C.
Makes sense.
That's simple.
All right. So now let's do an example. Okay. And the example we're going to do is off an impedance transformation. So this is a pretty simple example. Let's say I have a voltage source, and it's a sinusoid. We're going to make sure we're living in the phasor, and the domain in which phasor analysis actually makes sense.
I guess once we start giving them circuits that have the phasor V and I, we're telling them we've made that choice for them.
Right. That's right.
It's been properly cast.
Exactly. Okay. And we've got a resistor in series with an inductor. Well, we can transform that into the phasor domain. These are series components, so we're going to just add the impedances together. And so we'll model this then as a voltage source in the phasor domain driving through an impedance, and the impedance is going to be the sum of the impedance contributed by the resistor and that contributed by the inductor. So that's just going to be R1 plus J omega L1. Pretty easy. It's not very difficult at all.
That's right. They add in series just like you would resistors. That makes sense.
Now I can do another example where I have a resistor capacitor, and I get the same deal, except now the capacitor impedance is 1 over J omega C. So I would get, Michel, what do you think it would be?
Okay, so it would be R2 plus 1 over J omega C2.
Exactly, that's right. Now,
but that's not what you have written there.
That's not what I have written there, because I had 1 over J. Well, you know that 1 over J can just be written as minus J.
Of course I do.
Yeah, you should know that, Michel. All that education.
Yeah, so definitely when you've got a J in the denominator, and that's you can substitute as a minus J at the top. You can convince yourself of this with Eulers if you want, but
yeah, you don't even need Eulers to do it, right? Because if J is the square root of -1, that should be true.
Yeah.
Okay.
See? That's all that education.
Yep. Okay, so that's not so hard. That's fairly easy to do, and that's an RC. And the last one we can do is an LC. Okay, and in an LC, what we have is a
it's going to be J omega L plus 1 over J omega C.
Yeah, that's right. J omega L plus 1 over J omega C. And again, we can move the omega to the top by making it, move the J to the top by making it minus 1 over J, or vice versa.
Oh, right? I see. And then that highlights the fact that
right.
This is purely reactive, and so you get J and then the reactance.
Right. Now, the reason we like to do this, by the way, just to be clear, the reason we like to move the J's and collect them is when we start doing more complex circuits and doing analysis, it's much easier if you can sort of isolate the J's and isolate the real terms. And you're absolutely right. So let's think about it. Michel, This has an impedance. In other words, it has both a resistance and a reactance. This has an impedance. What about this?
Well, it has an impedance, but it has a zero real part. So
exactly. It's a
purely
pure
reactive.
reactance. It's a purely reactive impedance.
There's no loss element in there.
That's right.
Cool. All right, pretty easy. So voltage and current division work just as before. So in the same way, when you had two resistors here, if you recall, in the time domain with resistors, you would have that the voltage across this resistor was R2 divided by the sum, R1 over R2.
Right. So that's our old voltage divider.
Yeah, and you can go back and remind yourself of how we solve for that if you want, but basically the same is going to hold. V2, the phasor V2 is going to equal the phasor source Vs times Z2 over Z1 plus Z2 in this case, and Z1 over Z1 plus Z2 in this case.
And so that makes sense, this voltage division. Could we also do current division?
Aha! You must have prepared these slides. So, in fact, that's right. This phasor current will split between I1 into I1 and I2, and the magnitude of that will depend on the admittances in this case. And so in the same way as before, you had the admittances kind of dividing the current for you. So admittance 1 divided by the sum of the admittances times IS gives you I1, and the same for I2. Same thing holds in the phasor domain.
Makes sense. So having said that, let's see if we can apply some other techniques. So we can, in fact, apply all these sort of linear circuit analysis techniques that we learned before for DC to this case. In other words, we can do things like superposition, we can do Thevenin's and Norton's. And just to give you an example, we'll do a problem that we'll try to find the Thevenin equivalent for. Okay, so here's the circuit that we're going to do as a Thevenin equivalent example. So what I want to do is I want to represent this circuit by a voltage source and a series resistor, or what?
Well, my guess is that you're going to have some series impedance which has a resistor and a
that's right,
resistance and a complex part of reactance.
That's right. So in a Thevenin form, in the phasor domain, we'll have a Thevenin source and a Thevenin impedance. Okay. So that's what we're going to do it, and we'll finally give the answer in the time domain. So here's the circuit we're going to analyze, and I've specified the voltage source, and the voltage source I specified as being 10 cosine 10 to the 5t. So there's no phase shift to this voltage source.
So the phasor equivalent of that, when we transform that, is just going to be 10.
Correct, exactly right. So it's going to be a 10 volt source. Now, I'm going to transform it, but I'm going to go do one step immediately, and I'm going to transform directly into a Norton equivalent, okay? And the Norton equivalent is going to be that phasor 10, now, but I've got a 5 ohm series resistor, so that's 10 over 5. So the Norton phasor representation of that current source is going to be 2.
Okay, and then the resistor becomes a parallel resistor.
And the resistor becomes a parallel resistor, but resistors stay unchanged, so it just becomes a parallel resistor of 5.
Now, what about these other impedances?
Well, for the other impedance, it's pretty straightforward. I've got a series combination of a resistor and inductor, so I'm just going to put those in series to form an impedance equivalent Z1, and that's going to be 6 from the resistor plus J8. And the J8 comes from the fact that the impedance of the inductor is
J omega L.
J omega L, and omega was 10 to the 5, and the L is 0.08 millihenries, so that's 8 times 10 to the minus 5. So I've got Z1 is equal to 6 plus J8. Similarly, for the R2-L2 combination, I'm going to represent that as Z2 as 3 plus J4, because that's 4 times 10 to the minus 5 times 10 to the 5.
Got it.
Now, the capacitor is a little different, because the capacitor has R3 and C. So the R, of course, stays as 2, but the capacitor impedance is what, Michelle? So
it's plus 1 over J omega C,
right,
or minus J over omega C.
Correct. Okay, so it's going to be we like to move the J's to the numerator, so it's going to be minus J. And the omega C, well, omega was 10 to the 5, C was 10 to the minus 6. So omega C is what?
So it's omega C is going to be 10 to the minus 1, 0.1, so 1 over that, you get 10.
Exactly. So I get Z3 is equal to 2 minus J10.
Easy enough.
Okay. So maybe you can take the next step, Michelle.
All right, so let's start the next slide with this same circuit, so just kind of carry it over. So this is what Vivek just did. Now, I would say these two are going to be in parallel, so that let's come up with the equivalent impedance for these two things in parallel. And we will not do all of the math for you. You follow the same rules for parallel resistors and so on. So if you take 5 in parallel with 6 plus J8, okay, you're going to get this equivalent impedance.
Okay, so that's just the reciprocal of the sum of reciprocals, but the math is a little more hairy because this is now being done with complex numbers.
Yeah, they're going to have to, you guys are all going to have to get used to doing this, either, as Vivek said in the last module, all in rectangular form or all in polar form, whichever you like. We will, of course, in the courses, show you little tricks for doing them. For example, if you do them all in rectangular form, we can teach you that. But we assume you've seen this in your math courses. So now let's see. Let's carry this over to the next slide. But what do you think we're going to do here?
Well, my guess is I'm going to now go back. So I want to ultimately combine this z1 prime with the z2. So I think what I'm going to do is I'm going to transform this to a Thevenin equivalent.
That's right.
All
So
right.
Here we go with the same thing.
Let me try it.
All right.
Okay, so go for it. And here we see now we do the Thevenin transformation. So I take this 2 amp source and I've got the Norton resistor in parallel with it. So I transform it into a Thevenin source where I'm just basically taking this phasor current and multiplying it by this Thevenin resistance, and then the Thevenin resistance moves from a parallel to, in the Norton case, to being a series in the Thevenin case.
That's right. And notice there's a notation here which says ZS, even though the impedance is Z1. This is just to reflect that this is the actual Norton expression for the source terms.
That's right.
Don't go hunting for a ZS somewhere in the circuit.
Right, and so all we did is we took 3.51 plus J 1.08 and we multiplied by 2.
That's right.
Okay, and that's where you get this.
And then that impedance just went up there.
All right, and so now we've got a nice situation where we have these two in series. So what do you think we're going to do, Michelle?
We will add them, and I assume that it's going to be 3.51 plus 3, which will be 6.51.
Right, so here's what we've got. We've got these two,
Uh-huh.
and you're going to add them together.
So you'll get 6.51, and then this will be 1.08 plus 4, so 5.08. And this is the series combo. Now we've got this. Now what are we going to do?
All right, well, now I'm getting close, okay? So now what I want to do is, I think this is good enough. I don't need to simplify this anymore. I can actually start working out the Thevenin equivalent.
Okay, all right.
And so let's go ahead and set that up. So here's that circuit that I had, and if you remember when we taught you about Thevenin and Norton equivalents, we said there's various techniques. So to find the Thevenin equivalent, I need two things. I need to find the equivalent voltage,
The
and I
Thevenin
need-
voltage,
the
yeah.
Thevenin voltage, and I need to find the Thevenin resistance. So for the equivalent, for the Thevenin equivalent voltage, what I can do is just look into the circuit and find the open circuit voltage, right?
Oh, that's right. Following that method, we
Yeah.
could look for the open circuit voltage,
And
and that
that's
should
the-
be the Thevenin voltage.
That is going in all cases that's the Thevenin voltage,
Uh-huh.
and the fact that this is in phasor domain doesn't change that. I still analyze it the same way. So how would I do that? Well, that's fairly easy. This is just a voltage divider, right?
Oh.
So I would just use the voltage divider form to find the voltage between A and B.
So let me see, without doing all the math, what you're saying is that the open circuit voltage will be Vs times 2 minus J10 divided by 8.51 minus whatever 10 minus 5.08 is.
Yeah, which is
4.92.
yeah, you're right.
Okay.
All right.
So, and that's fine, and that's just a voltage divider.
Right. Now, we have various techniques we taught you for figuring out the Thevenin resistance, but I'm going to say that since this one is a system that has only an independent source, a really easy way to do it is to just turn off the independent source and find the equivalent resistance, okay? So if I turn off the independent source, since it's a voltage source, it becomes a short, which means these two resistors just go in parallel. So what I can do is find the Thevenin resistance as the parallel combination of this source resistance and the Z3 resistance, which we do over here. And it works out to be just 8.42 minus J 1.59 ohms. Okay?
Oh, I see. So, okay, so once you figured out what that is, you went a step further and you decided to show them how you could break this sort of complex term into actual two physical components.
Correct. And the reason I can do that is the 8.42 is real, so I can show that as a resistor. And the minus, so the fact that it's a minus sign, minus J 1.59, the minus should indicate to you that it's a good way to model it is a capacitor, because the minus J is equal to 1 over J.
Right, and so
Right.
the 1.59 must equal to 1 over omega c.
Exactly. And I know what omega is, right? And I know what omega
10 to the
is,
fifth.
so it's 10 to the 5th, so I can plug it in and calculate it. It works out to be 6.29 microfarads.
That's cool. And
Okay.
then I assume this source here is the time domain little voltage divider thing we just did a
Right.
minute
So
ago.
we calculated the voltage divider values. You just transform it back in the time domain, and you're done. You got your Thevenin equivalent.
Wow, so this is the Thevenin equivalent to that circuit. It's pretty cool. So you've got, okay, let's think about this. The Thevenin equivalent voltage has a magnitude, kept the same frequency, and then there's some, weird phase shift that came from solving the problem.
Right,
Okay?
and the phase shift came from the fact that there was a complex impedance That had both the real part and an imaginary part. In other words, there were resistive elements and reactive elements that we were forming an equivalent circuit for.
Oh, that's right. If you didn't have that, you wouldn't have gotten the phase shift. Maybe you've gotten this change, but not that.
Right.
Okay, that's perfect. And then, of course, the Thevenin impedance has a real part in the capacitance, and because we can tell whether it's a minus or a plus, we know whether this is a series capacitance or a series inductance.
Exactly.
This is pretty cool. Okay, so the last thing we want to do in this module is kind of a graphical, just show you something graphical. It turns out that this does lend you some intuition when you're thinking about things that you think have phase relationships that are meaningful. I tell you, in my experience, I found this to be the most interesting in the context of power distribution systems, because power distribution systems, the phase shifts between different things become very important. And so we're only going to do baby steps here. We're just going to show you in 2 slides, just graphically, the same thing we've already showed you in math, and we're really not going to push much farther for this course. So what we want to show you is something very simple. If we were to plot on the real and imaginary plane, right, same as before, if we were to plot the relationship between the voltage and current across a capacitor, we would notice something interesting. So first, let's assume that the voltage on the capacitor is purely real. Okay, that's not very difficult to do. So we'll assume that this is a purely real VC. So if that's the case here, then VC times J and then this omega C. But what it means is the magnitude will have changed, but there's a J multiplied by a purely real number. C is, of course, purely real, and so is omega, which means that the current must now be purely imaginary.
I see. So now what you're doing is you're taking advantage of the fact that the relationship between the current and the voltage in a capacitor is related to the fact that the impedance is 1 over j omega c.
That's right. I just rewrote basically the 1 over j omega c business right in this equation. So what that shows me, in the case of VC being purely real, it shows me that I is purely imaginary. But what the main point of this little the thing is that you have a 90-degree phase shift between the two.
I see. So now the current is 90 degrees in front of the voltage.
Exactly. Now, for an arbitrary case where VC might have an imaginary component, is not perfectly horizontal, what will happen is I will still keep that 90-degree phase shift. So if now VC is, say, up here, maybe it has a 45-degree angle there, your I would be where?
Your I would be 90 degrees leading that, so it would be in the second quadrant.
Right. And so this is always true. This is a really neat little graphical thing to see. It is always true that the current in a capacitor and a voltage capacitor have this phase shift from each other. Always.
90 degrees.
90 degrees, and in this particular leading lagging configuration, no matter what the actual value of it is, the current will then map the other way.
Got it. And I'm guessing the inductor is going to go the other way.
It's exactly flipped, just like everything else with inductors. And so again, if the VL is perfectly real on the inductor, because we know that IL, basically J omega L IL equals VL, basically this thing here, then this will always be, for a real VL, you get a minus imaginary number.
Okay, got it. Makes sense.
Pretty easy. Same thing. This I will always be behind this VL. Now, so, okay, big deal, right? So what's the use of this?
Well, before we move on, I've got to try resistors.
Okay, what do you think a resistor is?
I think a resistor will have a V and then
Let's say
I
if the
that
V is
will,
purely real.
will line on each other.
Yeah, if a V is purely real, lo and behold, the I is purely real. If a V is perfectly imaginary, lo and behold, it's perfectly imaginary. It is trivial. Okay, so now let's look at a little circuit as an example. So, Vivek, you want to try this out?
Sure, I'll give it a shot. Okay, so here we have a circuit, and it has a voltage source that's set up, and this source we've set up as it's 20 e to the j 30. Okay?
So it's already in phasor.
It's already written in phasor form, and we've accounted for the phase shift in it. And the circuit that we have has a resistor, a capacitor, and an inductor in series. And we've provided the values for you, and we've already given you the phasor forms. Okay, so we've given you the impedances. So the resistor is 8 ohms. The impedance of the capacitor is minus J8. The impedance of the inductor is J2. All right? So we've given you that. Let's go ahead then and figure out the current. Well, by Ohm's law, we know that the current is going to be Vs divided by R plus J omega L minus J over omega C.
Okay, so let me see to set up the next slide. You're saying is we've got a source that's going to have a magnitude and a phase shift.
Yep.
That's going to give rise, because it's all just one loop, to a single current that runs through everything.
Right, and the current is the same through all of them.
Right, and that it'll be the same through all three components. That will have a magnitude and its own phase shift.
Correct.
Okay, and that'll be determined by this equation.
Yep, we can solve this to find it.
Now, because we know that inductors, resistors, and capacitors have different relationships between voltage and current, for that same current, each of these will have a different phase offset for their own voltage.
Right. So let's go ahead and set that up, okay? So what we can do is we can do the first step, which you talked about, which is we can calculate what the current is, okay?
Okay.
And now, just so you see how that works, we plug in the voltage in the top, and that's in polar form, and then we plug in the individual reactances and resistances in the bottom, and so that gives us a rectangular form. So what often makes sense is the first thing to do is to go ahead and calculate this into a single form, okay? So we can do that. We can convert the rectangular form to a polar form, and then we calculate the current.
Okay, so the current's going to have a magnitude of 2, phase shift of 66 degrees. The original source voltage is 20 and a phase shift of 30.
Right, so you'll notice that one of the consequences of us having a complex impedance was the current and voltage in this, the current and the source voltage are out of phase with each other.
And yeah, and that phase was due to the action of all these components.
Further, you'll notice that this phase shift is not 0 or 90, it's sort of in between. And the reason for that is that's the net consequence of both inductors and capacitors, and of course the resistors as well.
For the amplitude. Okay.
All right, so let's go ahead, Michelle, and why don't you set up the graphical analysis?
Right, so then this was the sort of punchline of the whole thing. Having figured out that I equals this, we can now plot the source voltage, the resultant loop current, and then the voltages for each of these on our plot here that we were doing 2 slides ago. So here's the source voltage, 20, 30 degrees, right? We had that in the previous slide. Okay, magnitude 20, phase shift 30 degrees. The current turns out to do a magnitude of 2, phase shift of 66.87 degrees.
And so that represents the phase shift between the source. The difference between those two vectors represents the phase shift between the source and voltage and the current.
Right, on these two vectors.
Right. Now, it's a key point that this current, because of current continuity reasons, this current flows through all 3 components. That is, in fact, all 4. The source, the resistor, the capacitor, and the load. And the inductor.
Right. Now, Vivek, because this is your favorite topic, how would you figure out the phase shift of the resistor relative to the current through the whole loop?
Well, it should be in phase.
Whee! There it is. And of course, you multiply by the resistance value 8. 2 times 8 is 16. So you get 16, but the same exact phase shift. So they line up. The current going around the loop is always in phase with the voltage on this resistor, which makes sense.
I see, I get it. So what I'm going to do now is for each of these, I take the current and I multiply it by the respective impedance of that element.
That's right.
So for the resistor, it stays in phase since the impedance is real.
Right, but when I do, say, the inductor...
Okay, it's going to shift by 90. It's going to lead in one case and lag in the other.
Right, here we go. So the inductor goes to here, and the capacitor goes to there. You can see it's a 90-degree phase shift in both cases. Just one leads and the other one lags. And this will always be true. Basically, this thing will just, you can rotate it however you want. These relationships will always be true.
Got it. So now this is kind of neat because you see various things here. One is when you have these complex impedances, the current and voltage, the current and the source voltage can be out of phase with each other. In fact, they commonly are. And further, that if you look at the individual voltages across the individual components, those may have leads or lags with respect to each other as well.
That's right.
So that's a good point to end. We've now finished a basic overview of phasors and worked through some examples. We encourage you to do more examples because dealing with complex math often just takes a lot of practice.
Yeah, I agree. This is the real thing most of you will have to do for the next week or two is really just sit down and just practice your complex math. Make sure you get it. Okay? See you soon.